Thank you, Amber. So it is May 14th, 2025, Physics 7. And let's take a look at our schedule. I changed it. Here you go. This is my, oh, I need to share first, right? Screen one. Here you go. And cut. Okay, right in here. Here is the schedule. Today is the 14th. What you see here in this column is the week number and the meeting number, okay? So week number one, meeting number one, week number one, meeting number two, and so on. Every holiday, there's no meeting, right? Let's see. But exams are considered meetings. Exams are considered a class meeting. So today is meeting 24, week number 14. And meeting number 14, week number 24. There is anybody else coming here? Nope. And now let's take a look at the schedule again. Here you go. Well, the exam is scheduled for the next Wednesday. And then soon after the Wednesday, we're going to have a holiday. Do you want to do the exam on Wednesday, the next week? Think about that, okay? You don't have to decide right now. And when I take attendance, 1 hour from now, I will ask you if you want to postpone the exam or not, okay? We have, like I said, we have this opportunity to postpone the exam to the other Wednesday. The only problem, let's see. The only problem is that it's going to be 1 week before the final, okay? But on the other hand, it's going to be after a holiday and I'm going to have more time to study. Okay? So think about that and let me know what you think. Well, I'm going to wait for more students to arrive so I can hear from most of you. So here we go. One, think about whether here you go. The exam 3 is scheduled for next week, the 21st. Okay. Just before a holiday. Think about whether you want to postpone the exam for 1 week. Think whether you want to postpone this exam for another week. Okay. Today is lab 6, right? Lab number 6. But before we will continue looking at relativity, special theory of relativity. Special theory of relativity. And just be reminded of the two postulates of Einstein. It's not difficult to memorize them, right? Here you go, relativity postulate. The laws of physics are the same in every, don't forget inertial frame of reference, are the same in every inertial frame of reference. And what means inertial frame of reference? Inertial frame of reference, a frame of reference that is moving with constant velocity.
Professor, I have a quick question for you.
Yeah, go ahead.
So, just to confirm, was the exam pushed back from like a week ago? Because I could have sworn that today was going to be the day for it.
No, it has always been this exam. Oh, you mean the third exam?
Oh, okay. It's okay.
Okay. No, it has always
Okay,
been
that makes
scheduled
sense.
since the very beginning. Okay.
That's fine. Okay, thank you.
Okay. So, anybody else wanna ask a question? Uh, okay. So here you go. Initial frame of reference. The frame of reference that's moving is constant velocity. Okay, so examples, right? The inertial frame of reference. Example of inertial frame of reference. An example of inertial frame of reference. Inertial frame of reference. Your car moving with constant speed in a straight line. Okay? If you're moving your car with constant speed in a straight line in the freeway, right? That doesn't have to be in the freeway, but you are in a inertial frame of reference. The moment you accelerate your car, the moment you change your speed or the direction of travel, you accelerate your car, and during this time interval, it is no longer, it's not no longer, right? But it's not an frame, inertial frame of reference, okay? And make sure the car is moving also in a nice flat pavement. Okay, if the car start to jump back up and down, you also are introducing an acceleration in there. So that's what the theory of relativity is all about. It applies only to inertial frames of reference. And there are, well, those two simple postulates have some unexpected consequences, very important unexpected consequences. Okay. So I like to say that the consequences of the two postulates, even though they look so harmless, they're not harmless. They have some overwhelming consequences. Overwhelming consequences, okay? These two simple postulates, these two apparently simple, right? Let's put it this way. Apparently simple postulates have some overwhelming consequences. I'm going to talk about the consequences and then we'll prove as much as we can mathematically. Okay? One thing is to say that the speed of light is the same irrespective of their relative. The speed of light is the same is irrespective to the relative velocities of two different frames of reference. Okay? Another thing completely different is to work out the consequences of these two postulates, especially the second one. Okay? Another completely different thing is to work out the consequences of these two postulates, especially the second postulate. And I'm going to surely some of the consequences, and then we're going to prove as much as we can, okay? One thing that we discover is that there is this phenomenon of time dilation. And all those weird type of consequence has been verified experimentally, okay? Okay, time is observed to flow different from one inertial frame of reference to another. Okay, in other words, a clock in your inertial frame of reference will run faster than another clock attached to the second inertial frame of reference that's moving either towards or away from you. Okay, someone in the other inertial frame of reference is seen to age more slowly. That's what it means. And that gives rise to this gives rise to the twin paradox. Okay? And the twin paradox is the following. In the twin paradox, we have two twin brothers. Okay. One becomes an astronaut, and the other stays on Earth. Stays on Earth. The first, the astronaut twin, right? The astronaut jump into a rocket, jump into a rocket, and fly to another distant planet, and come back. For the twin to do that, for the rocket to do that, it's going to be an inertial referential frame only the way back to the planet. When he turns around, right? That's a small amount of time that the rocket turns around. It's not an inertial frame of reference for another planet and come back. When the astronaut arrives Earth, is found to be younger than his brother that stayed behind. Okay? So the clock of the astronaut was seen to move, but I'm talking about not just the clock, but also the biological clock. I'm gonna even say, the biological clock of the astronaut, okay? I'm gonna put it this way, is seen to move slower than the biological clock of the other twin, of the other brother. That's one overwhelming consequence. Okay, time dilation. Another important consequence here, which depends on time dilation, is the length contraction. Okay. the length of an object in a don't forget, it's not second inertial frame of reference, is measured to be shorter. Okay? So let's say, in other words, twin paradox. In the twin paradox, we have two twin brothers. Okay, twin number one, who becomes astronaut. Okay, twin number one, let me give a name to those twins, who becomes an astronaut, and twin number two, who stays on Earth. Okay. Twin number one, who becomes an astronaut and fly to a distant planet, and twin number two, who stays on Earth into his rocket and fly to another distant planet and come back and fly to this distant planet and come back. When he arrives, when he returns to Earth, when he returns to Earth, he's found to be younger than his brother that stayed behind. The biological clock of the astronaut is not seen, but is observed to move slower than the biological clock of the other twin, of twin number two, of twin two. And like I said, has been verified experimentally over and over again. Okay, experimental verification of this phenomenon, have been observed with two different clocks. Okay, one that stays on the ground, and another one that flies around the world in an airplane. You don't need to have a spacecraft to verify that. Scientists have verified that with atomic clocks. Okay, that's very precise, has a very large resolution, has a very good resolution, and because of its resolution, they can see those small time differences that occur due to the relativistic effect. One stay on the ground, and the other flies around the world in an airplane. Okay. Think about that, digest that. Let me give you a little bit of time before we get into contraction, right? Length contraction. Probably you have already seen something like that in the movies, right? And especially the movie Interstellar. Especially the movie Interstellar. Okay. And the other one is length contraction. Okay. The length of an object observed, right? Measured, not observed, measured, right? Measured by an observer. Let's say, let's put it in another way. Consider two referentials. Okay? One at rest one at rest, and another moving with constant velocity, right? The second referential has a ruler that can, whose length, right, can be measured by an observer in the first referential. In the first referential. In the first referential. Okay. Here you go. Length contraction. Consider two referentials. One at rest and another one moving with constant velocity. Moving with constant velocity. Okay. Both referentials have an observer moving with them. Okay. So you have an observer in the referential A, yeah, and you have a second observer in the referential B that's moving with the referential B. Okay. Second referential has a ruler. Okay, the second referential has a ruler whose length can be measured by both observers, like that. Okay. Consider two referentials, one at rest. Here you go. I'm going to put it here, referential A. And another one moving with constant velocity, referential B. Okay. The observer in referential, if the observer in referential B measures a length of 1 meter, right? Here you go. The observer in referential A will measure this same ruler as being shorter. Okay. The length that he measures depends on the relative velocity between referentials A and B. Okay. That's what length contraction is all about. Okay. And then we have the relativistic linear momentum. Okay. Must be here written to be conserved. Linear momentum is m times v, right? But in relativity, for linear momentum to be conserved, we have to redefine it. And your regular linear momentum is mv. Does not conserve from initial frame of reference to another. Okay. And in relativity, we have to define a different inertial linear momentum. Okay, what else? That those are a bunch of I listed a total of 5, okay? Relative velocities are also different. It's no longer the straightforward vectorial summation. Okay, if I'm moving at 50 miles an hour in the freeway with respect to the ground and another car is moving at 60 miles an hour, my relative velocity, according to Newtonian mechanics, is going to be 110 kilometers per hour. But in relativity, they don't sum that in a straightforward way. Okay. So example, right? Example. If I am moving at 50 kilometers per hour in one direction and another car is moving at 60 kilometers per hour towards me, according to Newtonian physics, the relative velocity, and don't forget 50, if I am moving 50 in one direction, 50 kilometers per hour with respect to the ground, right? With respect to the ground, we have to specify that is with respect to the freeway. Here you go, in one direction, and another car is moving 60 kilometers per hour towards me with respect to the freeway as well. With respect to the freeway as well, according to Newtonian physics, the relative velocity would end up being 110 kilometers per hour. However, according to relativity, the relative speed, not relative velocity, the relative speed, right? Better. Speed would be less. 1, 2, 3, 4, and one more important result of relativity that you may already be familiar with. Objects have a rest energy. Okay? That's called the relativistic energy, which is given by mc squared, the mass of the object, velocity of the light squared. What does it mean? This means that there is an equivalence between mass and energy. Energy is supposedly, in which in Newtonian mechanics has no mass at all. Okay? So those are the 5 important consequences of the theory of relativity. Now let's prove the first one. Let us prove the first one. The first one we prove by using the concept of light clock, okay? The first one, I'm going to prove the first one using the concept of light clock, and the second postulate and the second relativity postulate. Think about the timepiece, not just your regular mechanical or electronic timepiece, but one that you use the speed of light to keep time. We call that the light clock. This is a very nice thought experiment that we can do to derive the consequence of special relativity for the case of time dilation. Okay, and I'm going to introduce here the light clock. Here you go. Okay, here's my referential A in black color. Here's referential B in red color. It's slightly displaced, right? Here's the observer at rest with respect to referential A, and here's the observer at rest with respect to referential B. Okay? They're moving with respect to each other, okay? They're moving with respect to each other with constant velocity. I'm using the same notation that I used in my first physics course. Velocity of B with respect to A. Here you go. The velocity of B with respect to A. I don't need that. Okay, so here you go. I'm gonna play the movie for you, right? Here you go. B is moving away from A, okay? Going back, I have only 4 frames here for my movie. And the observer is moving together with the clock. What I have here is the light clock. This one here is the light clock. And what you see right in here is the photon. Okay, it's a particle of light. A particle of light that's moving up and down. It's being reflected by this light clock. The light clock has a mirror here at the top and another mirror here on the bottom. And somehow I managed to insert this photon here that's gonna move back and forth. Okay, watch it, this light clock as the referential is moving in the frame, right? Initially, the photon is right in here, the particle of light is right in there, but then a little bit later, the particle of light is a little bit higher in the clock, right? Because it has a speed, it's moving with the speed of the light. A little bit later, a little bit higher, and so on, right? Here you go. About to be reflected there at the top of the mirror. Okay, that's the concept of the light clock. That's the concept of the light clock. Okay. So keeping that in mind, the observer in B sees the particle of light moving just in the vertical direction, up and down, right? However, the observer in A see that this particle of light is moving not just in the vertical direction, but also in the horizontal direction. There is a combination of motions due to the relative velocity of the 2 referentials, okay? Let's write that down. Okay, let's write that down here right in here. In the light clock in the moving referential has a photon of light that moves in the vertical direction only for an observer in B, right? The light clock in the moving referential B, has a photon of light that moves in the vertical direction. That moves, that moves between the 2 mirrors, right? In the light clock. Okay, and I gotta define here, right? A light clock is a device that is made up of 2 mirrors facing each other and displaced by a distance d. Okay? Inside this light clock, we have a particle of light, a photon. This photon bounces back and forth between back and forth between the two mirrors. Okay? In referential B, the observer in referential B, here you go. The observer in referential B sees this photon moving in the vertical direction only, right? But an observer in referential A sees this photon moving in a combined horizontal, in the combined horizontal and the vertical directions, like that. So here you go. So here you go. That's what. Let's see if I have here. Watch right in here. Another movie. I'm gonna play you another movie. Here is what the observer in A sees, right? For the motion of the photon is going to move sideways and upwards as well, right? And that's gonna be the full period. When the photon goes back to the lower mirror, the amount of time that this guy times is gonna be the full period of the photon. Okay, now going back here, look now concentrate on this other one. The observer in referential B see the photon moving only in the vertical direction, right? Because it's moving with the referential. If we apply, right? If we apply the second postulate of Einstein, we are going to find that the period of oscillation of this photon, as seen by this observer, is going to be different from the period of oscillation of the same photon in the other referential, okay? So here you go. This photon travels upwards, these are according. Let's start with this one, referential B first, that's easier, right? Referential B is easier, okay? The photon moves twice the distance between the mirrors, 2D. Let's put here 2D. The period measured by this by this observer is going to be twice this distance divided by the speed of the light, right? Okay, makes sense? That's the easiest part. Now, what's a little bit more difficult is right in here, okay? The period that this guy measures is going to be the distance that he sees the photon traveling, which is this plus this. I'll call that length of C with respect to A, right? C is the clock, and C is the photon, and A is the referential, that's at rest, divided by C. And now you can calculate this L of C over C with respect to A. It's going to be this distance here, D, okay? I put uppercase, should be lowercase d. D squared, right? And this other distance here is going to be VT. Okay, VT. Make sense? And what we end up getting is just a right angle triangle multiplied by 2, right? This distance here is VBA TCA divided by 2, right? Plus D, oh, don't forget the square, plus D square. And I'll derive that, here you go. In the in the notes. Okay. Okay, here you go. There's so many. This one. The reference shall be the period of your light clock measured by the observer B is what? Twice the distance. I'll put that lowercase d. C delta T naught. Okay. Which I'm going to say, delta T naught, I'm going to call the period of the clock as measured by the observer in referential B. And then this delta T naught, I'm using delta T naught because that's a notation that people usually use in the books, okay? You can here write that relation as being 2D divided by C. So that's the period of the clock as observed, as measured by observer B, okay? And then you gotta do the same thing, but you're gonna get a different result. However, for an observer in referential A, the period of your light clock in B is going to be different because the speed of light is the same no matter the referential, right? The second postulate. So here you go. Let's see if I can. Yeah, I got it. Right. So the length that this photon travels is going to be, let me do the mass here right? So it's going to be um, L, you go, CA, LCA. Let's see how I'm going to do that. Okay, that's okay. We can keep on doing that. LCA square. Let's see how I'm gonna call it the hypotenuse, okay? Hypotenuse, okay? It's better if you call it this way. The hypotenuse for H, okay? And then we relate that to the LCA, okay? The hypotenuse here in this case is going to be V of BA times the period of the clock C measured by the observer. Okay, I'm trying to obtain this length here, okay? The hypotenuse, that's what I call H. And what I have writing here, divided by 2, by the way, divided by 2 because it's half of the period, right? When the clock moves from here to here, it's just half of the period of the clock. And that should be squared. We're doing the Pythagorean theorem. Okay, plus what? This distance here that I'm calling D square, okay? But the whole length is gonna be, has to be, here you go, this length alone, right? Get out, here you go. Huh, strange. Okay. I'm gonna take the square root now. Okay, H, right? Now the whole length alone is gonna be twice H, right? H is this distance here. The whole length that the photon travels is twice this length, okay? So that I'm calling LCA. The length that the photon travels is going to be twice H or twice this square root, okay? And then what else can you do? And let's not forget that the period of the clock, let's see, LCA divided by the period of the clock must be equal to the speed of the light, right? Length divided by time. Okay? See right in here. See right in here. And I can here write LCA as being C TCA. TCA. Right? And now I'm gonna get this equation here that you have. Oops, what did I do? This equation here. I'm gonna make it equal to this other one. Okay, what I have here go. LCA is equal to that. Okay, what else? What else do we do? Remember, we want to calculate TCA, right? TCA is here, and TCA, the period of the clock as measured by an observer in referential A. Okay, so what I have to do, I have to square both sides of this equation. Okay, and when I square both sides, you go. I'm just gonna copy here and paste there, square the side. Okay, 4. The 2 is gonna be squared. Oops, 4. Okay. What I want to do, I want to solve for this guy here and see what we get. I am going to square everything here. Okay, and here as well. Okay, we're gonna square this one as well. Oh, no. Okay, square this one. It's gonna be 4. And okay, with the step-by-step derivation. I'm going to expand this 4 is going to cancel with this other 4 right in here. That will multiply my d square. I don't need the parentheses anymore. Okay. I'm gonna pass the first term on the right side to the left. Notice that you are going to have a common term on the left side. Okay. And I'm almost over. Put that in evidence. Okay. And pass this to the other side. To the other side, here we go. And finally, we have this result. It's going to be 2D and the square root here. Square root right here. Okay, let's compare with the period, with the other period that we got. This period here. Note, see that they are different, right? They are different. We do have, I have 2D here and I have 2D here as well, but not here. Here I have C, here I have this square root of C minus VBA, okay? So what A is measuring a longer period. That's called time dilation, right? The time dilates according to the other referential. I can here write that in terms of the other. Oh, can here write that in terms of the other. Let's see how I'm going to do. Yeah, I'm going to put, I'm going to write that in terms of this value here, okay? So I'm going to put C square in evidence. Okay, that's a little mathematical trick that we learned. I'm putting the C square in evidence. I didn't change the equation whatsoever. And now that I put the C square in evidence, I can take it out of the square root, right? Here you go. And everything that's left is this square root term here. I'm going to here write it. I'm going to put the C here upstairs. And now I don't need the C here anymore. And now comparing this term with this term, right? With this term here at the top. Let's see. This term here at the top. We see that TCA is equal to TCB over that factor that you're seeing. And this factor, by the way, is less than 1. Because this square root is less than 1, VB is always less than C. TCA is going to be greater than TCB, right? That's what's called time dilation. TCA greater, I'm even going to say greater or equal. Because if it is at rest, TCB is going to be equal to TCA. Okay? That's the phenomenon of time dilation. Think about that. And by the way, this factor that you see downstairs here has a name in relativity. This factor, the 1 divided by the square root of 1 here divided by the square root has a name. Okay, this factor here, we give it a name. We call it the gamma factor. It shows up so frequently in relativity that we give it a name, a gamma factor. And this gamma factor, we can plot it. You can see the higher the speed of the differential, right? The larger the gamma, right? We can plot that. Let's see here. I am going to write it here.
Here.
Yeah? Someone was going to ask a question? Okay, so here you go. Gamma. Dimensionless, right? Gamma, let's see. V over C, okay? I'm going to plot that with respect to V over C, this term here, okay? VBA over C. It's never greater than the speed of the light. Started at 0, right? And let's get 0.1, 0.2. Let's go more data points here. 0.05 until we reach the value of 1. And now we have to, here we go, 1 divided by square root of 1 minus V over C squared. Okay? So we're going to plot that. At the speed of the light, the time is almost infinity. Okay? So here we go. We're going to plot that. The closer the differential is to the speed of the light, the longer is the period of your light clock. Okay? So exactly at V equal to C or V over C equal to 1, the period of the clock, the clock is going, the photon is going to be seen to be at rest by the other observer. Okay? That's the behavior. It all depends on the speed of the referential. The faster it travels with respect to the speed of the light, the more the larger the relativistic effect. Okay? That's the behavior. Okay, gamma. And I can format, chart design, add elements, axis, primary, axis title, primary vertical, primary horizontal. Here we go. This one is gamma. Let's see if I can get that in symbol. Yeah, I got it. Now I will make it larger so you can see it more easily, right? Numbers, don't put in general, but number. And I'm gonna put just one decimal place there. Here is V over C. VC with respect to A, right? Or even better, VB with respect to A, which is the speed of the referential with respect to A. Font, subscript, and let's not forget, it's not just VBA, it's actually VBA over C. VBA over C. I'm gonna need the font here, change it to normal. Oh, okay. Okay, now I can change it. Format font, subscript. Okay. And 24. 24. The units here is 1, right? Because it's meters per second divided by meters per second. Someone's trying to come in. Here too, the unit is going to be 1 because it's unitless unit. And I can put that in my notes. Okay. As V. As V BA approaches C, gamma becomes very large. Okay. That's, let's say, the magic of special relativity. Okay. So now let's take attendance and remember I should they use there? Why 19 here? Strange. Lecture, that's the lecture. Okay, I want the lab. Okay, here you go. Exam 3. Exam 3. Okay, Abir Ahmad. Are you there? I cannot hear you, Abir. Yeah, you just type there in
I'm here, Professor.
okay, good. So do you wanna keep the date for next week for the exam or you wanna postpone it?
Next week's good.
Huh? Next week is good?
Yes, next week is good.
Okay, no change, right? So next one, Nestor.
Here.
What do you prefer, next week or a week later?
Honestly, it doesn't matter. Either day, either or.
Either. Okay. Monte? Okay, yeah, okay. What do you prefer, next week or the other one? Can change it to next week. You prefer next week, right? Let's see. Later. Let's put later. And Isabella? Isabella there. I don't see Isabella here. Justus?
Hey, Professor, good morning.
Morning. What do you prefer
And
for the exam?
for the test, I would honestly prefer it if it was for next week, like the 21st.
Okay, let's see. Either next week or later. I didn't understand.
Let's do next week.
Next week? No change.
Yeah.
Okay, good. Next, Alexandra?
Next week is good for me.
Next week? Okay, no change. Next is Benjamin Carvajal. No change. Okay, good. No change. Next is Elizabeth Castellano.
Next week is okay.
Okay, good. No change. Natalia Cordoba. Here and next week is good. Okay, next week no change. And Jacqueline Delgadillo.
I can't do it next week because I have to walk the stage because I'm graduating from Cal State LA next week.
Okay, so Jacqueline, right? Delgadillo, you prefer later. Okay, and Jenny?
Here and no change. I prefer it next week.
Next week? Okay, no change. Okay, good. Next is Valerie.
Here.
Yeah. What do you prefer, Valerie?
Next week, please.
No change, right? Okay, Juan Escalera. Are you there, Juan? Here, either is fine. Okay, either is fine. Okay, Bianca Ellucky. Next week, okay. No change. Edwin Gonzalez. Next week, no change. Ellie Gonzalez.
Here and no change, please.
No change, okay. No change. Next is going to be Manuel Hernandez. No change, okay. Samantha Hubert.
I'm here, no change.
No change. No change. Next. It's gonna be CJ. CJ is not here. Next is gonna Amber. Let's see. Are you there, Amber? I'm gonna put a star here for Amber. Next is Adelie. Here, do you prefer next week or the other week? Adelie? Other week? Later. I'm gonna put later here. Genesis Lopez.
Hello. This week. I mean next week.
Next week, okay, no change.
Thank you.
Mary. Yeah, no change. No change. Galia. Are you there? No change. Okay. Ramon.
Here. No, I could do it the 21st.
Oh, I didn't understand. Is that no change or?
No change.
No change. Okay, thank you. Taylor?
I'm here and no change is fine.
Okay, no change. Taylor? Are you there, Taylor? Taylor, let's see. Oh, Taylor. Jeremy, sorry. Jeremy, Jeremy is not here. Stephanie? No change. Okay. Next is Leslie. No change. Jason?
Here and no change.
No change. Okay. Okay. Gemma Torres?
I'm here. No change is fine.
Okay. Okay. So we're gonna keep okay, we're gonna keep for next week the exam. And if you cannot make it, send me an email, okay? Even if you have emailed me before, send me again, and we figure out what you're going to do, okay? So let me write that down here. The third exam. Third exam is still scheduled for the 21st, 25. Okay, if you cannot make it this exam, let me know. If you cannot make it this day, send me an email. And okay, send me an email telling me why you cannot make it, and let's see what we can do. Okay. It's 10:50 right now. Let's take a break. Send me an email, even if you have already done so. Okay, send me an email, even if you already done so. If you have already done so, telling me why you cannot make it. Break is 10:50 a.m. to 11:05 a.m. Okay, so see you in 15 minutes. Stop sharing. Okay, so I'm back here. And let me stop sharing momentarily and I'm going to upload the report for lab 6. More students coming. Okay, so here we go. Okay, so I will start to upload your lab report. Let's see here. How is speed grader? Something wrong here. Let's see. Huh. Strange. Late missing. Let me see one thing here. Added. 28th of May. Okay. Okay, good. Problema. Let's see if it works now. Great, great, great. Huh, something wrong here in this thing. What's going on? Speed grade. Let's see what's going on here. Ah, yeah. Seems there is something wrong here with canvas. Sort, speed grader. Let's try again. Great. Huh. Ah, that's so odd. Mhm. Let me try something else here. Status. For some reason, I cannot upload it. Lab 6, looks like I'll have to send you by email. Okay. Let's see, sort, speed graded curve. Late missing excuse. That's so odd. Someone. Huh. Yeah, it allowed me. Why it's not allowing me to submit to a student here? It's strange. Let me refresh. Okay, let me try something else. I'm going to log out from Canvas. If I cannot submit that to you, then I'll have to send the spreadsheet by email, okay? One last attempt here. Okay. Great. Let's try it here. Here and no change. Okay. Thank you, Amber. Yeah, for some reason, it is not allowing me to assign. Oh, wait a minute. I think I know the problem. Okay, it looks like I finally found what the problem is. Signed. Yeah, assigned to everyone. It's assigned to everyone. Huh. Let me, I'm gonna delete that. Let's try it again from scratch. Okay. One more attempt. One more attempt. Let's see what's going on here. Assignments, external tool. External tool. Assignment discussion quiz, external tool. The external tool. Report. Due date. Okay. Let's see if it's assigned now. Assigned to everyone available 1 a.m. until 28. Okay. Everyone here has been assigned. Let's see if it I can upload now. Huh. Yeah, I'll have to send you. I'll have to send the spreadsheet by email. For some reason, it's let's try it here. This one. Yeah, for some reason that doesn't give me the option to upload here in Canvas. I do not know why. What a shame. I never had this problem before. Okay, so check your email. I'm gonna send, let's see. I'll have to do that one by one. Okay. Our courses. Okay. Uh-huh. March. Okay. Go back to here. Continue. Lopes. Lopes. Mission Street. Mission Street. Okay. Lab 6. Lab 6 spreadsheet. Okay, attached. Okay, so okay, so he go. I emailed the first group of students. Now the second group of students. Let's go. Yes. Yes. Array Lopes. Array Lopes. And Emma Torres. 6 spreadsheet. Attached. Let's see, someone is trying to come in. Let me help you out. Okay, now I'm going to. Okay, second group of students, check your email. Let's do another one here. See here. Send. Inbox. Send. Okay, let's go the next group of students. Motion. Next one is this one. Ideas and lock this spreadsheet attached. Okay, third group of students. Check your spreadsheet, check your email. Let's see. Search. Ballesteros. Escalera. Mary Michaelian. Good. For fourth group of students, let's look at the next one here. Let's go then. Okay. Beautiful. Okay. First group of students. Six. Okay. Fetch 7. Spreadsheet. Touch it. 6. Huh? Next, so 8, 8, 8. Castellano. Castellano. Hernandez. Hernandez and Jeremy Pittman. Jeremy Pittman. Let's see. That's going to be 8. 8 group of students. Let's see, almost over here. Córdoba, Samantha Hubert, and Stephanie Ramos. Stephanie Ramos. Okay, now the last group of students. At this point, most of you should have already received the spreadsheet, okay? All I have left here is 2 students, CJ and Leslie. Oh. Leslie. Okay, so I emailed everybody. And now we can start the lab. It's lab number 6. Lab 6. 8. Just type there in the chat box if you received it, the lab 6. Please, I want to make sure everybody got it. Yeah. Okay, just to ensure everything. For some reason, I couldn't upload this Lab 6 to Canvas. I do not know what happened. I'm gonna check with Canvas what's going on. And next time we hopefully we won't have this problem. Okay. Insert. Looks like everybody got right. Okay, if you didn't get, let me know. So let's start with Lab 6. Okay. And I need to start sharing the screen with you. Okay. So download the spreadsheet to your hard drive, computer hard drive. What we're going to do again, we're going to verify Ohm's law for a circuit. But now we did Ohm's law for a single resistor in the circuit. We did Ohm's law for two resistors in series, okay? And now we are going to do Ohm's law for two resistors in parallel.
Professor, I have a problem. I didn't get the spreadsheet. I was like refreshing the page, but no link like comes out. It just says like assignment, but it doesn't show like the link for the spreadsheet.
Did you check your email, Stephanie?
Yeah.
Okay, you didn't get anything by email, right?
Let me just double check one more time.
Yeah,
Maybe I didn't look.
check your email. Everybody got by email, right? Everybody else got by email.
Okay, I just saw it. Thank you.
Okay, it's in the email, right? Good.
Yeah, I have it.
Okay, thank you. So here you go, Lab 6. Okay, so what we did in the past, right? This is Lab 6. Lab 5 was two resistors in series. Lab 4 was one single resistor in the circuit. Just let me see, Amber Lopez. Okay, did you check your email, Amber? Okay, so you didn't get it? Okay, let me try it here. Lopez, you're supposed to be. Yeah, okay, so let me stop sharing the screen again. And now, okay, now, Lab 6 spreadsheet, attach it. Now you should have, Amber. Check your email in Canvas. Okay. Notes right here. Okay, so that's what we did, right? The lab 4 was a single resistor in the circuit. Lab 2, we verify Ohm's law with 2 resistors in series, and now we are going to do Ohm's law for a circuit with 2 resistors in parallel. So what we're going to do, we are going to find out the voltage and current data for different supplied voltage, just like we did before, but it's just a different circuit, right? After collecting the data, we are going to plot V along the y-axis and I along the x-axis. Okay? We'll compare the slopes of the graphs with the equivalent resistance of the circuit. Okay, download the spreadsheet from your email. Today is from your email. Okay. That's the first step. And what's going to be the materials that you're going to use? Well, we start with the digital multimeter. Okay, I'm gonna list them all. Okay, so 11:38 already. We spent too much time. I'm gonna, digital multimeter, 2 resistors, 1 power supply, 2 red cables with banana termination. Or the cables are used only for organization purposes. Okay, the color doesn't mean that the cable behaves differently. Okay, it's exactly the same cable, it just has a different color. And the color is in there just for organization purposes. 2 black cables with banana termination, similarly, right? The color of the cable doesn't affect the cable. 2 alligators and a proto board. And let me get this. App slides. Resistors in parallel. I am going to close this one. Resistor in parallel. Okay, we start with digital multimeter. Why do you need the digital multimeter? We need the digital multimeter to measure the resistance of the resistor, okay? So power up your DMM, resistance measurement. Okay, jack. 1 cable to the red cable to the red jack, the black cable to the black jack. Okay. And clamp the alligator to one end of the resistor, clamp the black alligator to the other end of the resistor, clamp the red alligator to one end of the resistor, right? 2 different, and clamp the black alligator to the other end of the resistor, measure your resistance. And then at this point in time, we are going to have our first data in the spreadsheet, raw data. Which is this one here, right? That's resistor number 1. Let's see. Oh, thank you. Thank you for letting me know. You keep on turning off, right? Over and over again. So here you go. Thank you for letting me know. And let's go back here to the notes, right? Here you go. Here are the materials, right? Digital multimeter, 2 resistors, 1 power supply, 2 red cables, 2 black cables, 2 alligators, 1 proto board. And here you go. I'm gonna repeat here again. Here you go. The digital multimeter is this one that you see. Okay, power it up, adjust it to read resistance. Red banana termination to red jack, black banana termination to black jack of the multimeter, clamp red alligator to one end of the resistor, clamp black alligator to the other end of the resistor, right? Measure your resistance, and we got our first measurement here of the resistance. Resistor number 1. Let me, resistor number 1. And next, we repeat for resistor number 2. Okay? And here you go. That's how you measure the resistance. Repeat for second resistor. And then, again, here you go. That's the second. I'm going to highlight with yellow color everything that is an actual measurement, okay? Just like I did before. Okay, so here you go. And now we are going to put the circuit together. Power supply. Okay, power supply and materials, procedure. Let me put the procedure here. Procedure. Measure the resistance of the resistance of the 2 resistors with the multimeter. Log their resistances in the spreadsheet using the proper number of significant figures. Use the table provided in the class to determine the right number of significant figure. You may need to convert the numbers in the table from scientific to numeric format. Okay, and now we are going to put together the actual circuit. Here you go. Turn on the power supply. Plug in one end of the red cable with banana termination to the red plug of the power supply. Plug alligator clip to the other end of the red cable. Okay, so here you go. Like that. Black cable and red cable. And here is the first resistor in the proto board. Okay? And here's the second resistor in parallel with the first resistor, also in the proto board. And here you go. We have this circuit established right in here. At this very moment, current is flowing from the positive through each resistor. First, reaching this point, the current splits, goes to the first resistor and goes to the second resistor. Okay? And the circuit closed down. It's better. I will leave this way. Okay? So here you go. Main current, the total current coming out from the battery, and this current is split into 2 values, I1 and I2. That's exactly what's happening here. Okay. Plugging one end of the black cable is the banana termination of the black plug of the power supply, right? And clamp alligator to the both ends of the resistor. Now turn on the DMM. Set the DMM to read voltage. Okay, so it's the next. This thing can be, either way, okay? That's what I mean here. It doesn't matter how, you cannot do that, but this you can do this, you can do in real life, right? What you cannot do is do something like that. If you do something like that, you're gonna burn your power supply because you are having, right now, you have a shortcut, okay? You cannot do that either, okay? Here you go, digital multimeter. Now the digital multimeter is going to be used to measure the voltages, okay? And here you go. Red jack of the digital multimeter to the positive end of the 2 resistors. Black jack of the digital multimeter to the negative end of the 2 of the resistor. Yeah, I am connecting that in series with resistor number 1, okay? And set the go. Set the DMM to read voltage, right? So he go. Let's copy everything here. So I don't have to keep on going back to the same thing. Okay, here we go. Red cable is banana termination into the red plug of the other end of the attached, black cable, set power supply to 10 volts. We are right here. Now that you set the power supply to 10 volts, you can measure the electric potential on the first resistor by the DMM. And that what we have right here, power supply set to 10 volts. That's the V1 electric potential across the first resistor. Okay. And next, measure the voltage. Okay, both sensitivity scale. And then you invert the polarity. Invert the polarity, you're going to get a negative measurement. And that, here you go. This one and this one. Okay. Next. Okay, and measuring voltage V1, always connect the multimeter in parallel. Okay, and now measuring voltage 2. We're going to measure the voltage 2, and you're going to see that the way we connected, you're going to get almost the same value, okay? Because those two resistors are in parallel. Here you go. And now we're measuring R2. Even though the points you're measuring changed, electrically speaking, they are exactly the same. It doesn't matter if you put it here, 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 here. It changes if you put here, 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 but not along this. I call that V2, but it's not going to be any different. Okay, so here you go. V2, right? Change the polarity. That's what we're going to see in the next one. Notice that the multimeter is still connected to those 2 points. And now the multimeter is going to be connected directly to the leads, to the jack of the power supply. To the jack of the power supply. And again, because all those resistors are in parallel, you're going to see the same result. Almost the same results, not exactly the same result, right? And that's what we get here for this 2, okay? Okay, now I'm sharing the screen, right? And then what do? We change the voltage in the power supply to 8 volts and repeat the measurement that we did. Change the polarity and repeat the measurement that we did. Okay. Change to 6 volts, right? Change the polarity. The next thing that's going to change is just 4 volts, 3 volts, minus 3, minus 4. We can skip all of that. And those are all my measurements. What time is that? 11:50. Okay, let's take a little break now. And any questions so far? Yeah, let's take a little break, right? So we don't get burned out. You go break from 11:51 a.m. to 12:06 p.m. Okay, and I see you in the next few minutes. Okay, at this exact moment, we measured all the electric potential in the circuit. Okay. If you look very closely, you're going to see that V1, V2, and V3 and V total, although they seem to be completely different measurements, they're very close to each other, okay? Analyze that in your spreadsheet. They're not going to be exactly the same because you never get the same measurement, but they're very close to each other. They're very close to each other. So, and that happens to every set of voltages right in here. What is not the same, what's not going to be necessarily the same, is those values here for the current, okay? And in order to measure the current, we have to come up with a different circuit. We have to break down the circuit that we have initially, right? And disconnect everything and start from scratch. Okay. Okay, we start with the power supply. Power supply set at 10 volts. Connect the positive of the power supply to the jack for the current measurement of the DMM, of the digital multimeter. Okay, and now we're going to put the digital multimeter in series, okay? The next they're gonna do connect the black jack of the multimeter to my 2 resistors and close the circuit. The resistors are just like that, right, in the proto board, and we close the circuit. Okay, here you go. Whenever you measure the current, like I said before, you have to use a different circuit in the DMM. A circuit, you have to use a circuit inside the DMM that's different from the circuit to measure the voltage, okay? That's why we have 2 different jacks here. One is for measuring voltage, measuring resistance, okay, and frequency, depending on how fancy your multimeter is. And the other is a separate circuit that's to measure only current. That's why you have to set up your multimeter in series. And here you go. That's how it looked like as a schematic diagram, okay? And here's the circuit for measuring the total voltage. When the multimeter is placed right in here, it's going to measure the voltage, the current coming out directly from the battery. It's going to be the highest of all currents because the circuit is in series. In series, no, in parallel. It's in parallel. And let's oh, it's right in here. Here you go, measuring the current. Disconnect everything, start from scratch, adjust the DMM to read current, connect the red jack of power supply to read, to red jack, okay, of the ammeter. Connect black jack of the DMM to one end of the resistor. Connect the other end of the resistor to the power supply to close the circuit. Okay. And now we are going to repeat the steps that we did before. And you know what? I'm going to go back to a different format. Otherwise, it's going to be a little bit confusing. Yeah, let's do that. It's not going to be very nice, but that's okay. Here you go. Was trying to organize it in a better way. Yeah, I did organize it in a better way, but then I have to do something else that's going to take a long time to fix. So let me go back to what I had before. Okay, now we are measuring the current. Okay, I'm going to do like that. Give a little bit of space. Okay. Adjust your DMM. Okay, we saw that in the drawing. Connect blackjack. And what is here? Repeated steps 2O, 2P, 2Q, blah, 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 right? We're measuring the current. We're changing the voltage and measuring the current, okay? So 2O is this one, set power supply to 10 volts. See that? That's 2O. Set power supply to 10 volts. 2P, you know, we're going to measure I1. 2O, 2P, 2Q, 2R, 2S, okay? So here you go. And you put it at 10 volts here, measure the current, that's the total current, okay? Put at 8 volts in the power supply, measure the current, 6 volts, 4 volts, 3 volts, and then invert the polarity, okay? -3, -4, -6, blah, 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 and then we get that one here. At this point in time, you can already start plotting the total with IT, okay? So you have our 2 sets of data to plot our first graph. And that's the next one. We are going to, okay, invert the polarity, okay? And now we gotta measure the current I1 passing through the second resistor, right? At this point, what we did here, we placed the multimeter right here coming out from the battery. Now we're going to put the multimeter right here at R1 in this branch of the, and then here you go. Connect, here you go, connect to the positive. Let's see. Yeah. And then we do something like that, okay? And be very careful what you do next. At this very moment in time, we have just one resistor, but we do something like that to get it well organized, okay? To get it well organized. So what we're going to do now, we are going to connect the positive of both the power supply and the multimeter directly to R2, okay? That's what we are doing here. And when we do it like that, the ammeter is going to measure the current only through the first resistor. Okay. And then you invert the polarity, right? Change the power supply voltage there, just like we did before. And then, okay, and here you go. Now we have I1 and V1. We can plot our second graph. Okay. And finally, we move the multimeter to the branch of the second resistor. You start from scratch all over again. Okay, here you go. Power supply, multimeter, and now what I'm going to do, I'm going to connect just to the R2. That's a very good way of putting together the circuit, okay? First connect to R2, and then make sure that the branch that goes to the first resistor does not pass through the multimeter, okay? And how do we do that? Just by coming out from the positive of the multimeter. Initially, right, when we are measuring I1, we had something like that going to the resistor number 1, okay? But now we have to put it here. Here you go, R1, and close the circuit. Okay, and do all the measurement, invert, right? Invert the polarity. And let's see, no, I don't want that. One on the top of the other, I don't want that. Here you go, better. Okay, invert the polarity, and here you go. we are done with the
Oh my God,
measurement.
you look like a señora.
What?
You look like a señora with those shorts.
Let me see. Someone is talking here. Here you go. Okay, now everything else, I1 plus I2 is just a result, a mathematical result. A mathematical result that must be very close to the total current here. And here too, a mathematical result. I'm going to highlight it with a different color, so you know it's something different. And now let's go ahead and start plotting nodes. Plotting your graphs. Okay. Here you go, plotting your graphs. V1 along the y-axis, I1 along the x-axis, V2, I2, V total, I total. Okay, so let's do that together. Oh, before we do that together, let's see if everything. I'm gonna call you one by one, just like I. Today is the 14th. Insert. Okay, let's see. So first, I understand everybody got plot graphs, okay? So let's plot it together. Here you go. Doesn't matter which one you plot first, okay? If you want to plot the V total first, it's okay. Plot V total and with I total here. Insert, and here you go. And it goes through the same same procedure, add trend line. Okay. I'm sharing the screen this time, right? So let's see. Let's start with Abir. Did you manage to plot the first graph? Hello, Abir.
Yes.
Yeah, you did?
Not yet, no.
Okay, you're working?
Yes, I'm still working on it.
Okay, so let's put plot G1, plot G2, plot G3, right? Yeah, let's see. G3. Total of 3 graphs. Let's see, Nestor, did you plot your first graph?
Yeah, I just barely done the first graph right now.
Okay, what about the second one?
No, not yet. I'm working on the second one.
Okay. And let's see, Monte, did you plot the first graph? Is Monte there? Let's see if Monte looks like Monte has left. Okay, next. Next is Isabella. Isabella, did you plot your first graph? Let's see if Isabella is here. I don't see Isabella. Okay, let's look. Next is Justus. First graph, okay, good. And don't forget to get the regression equation, okay? Working on the second, that's good, thank you. Next is Alexandra. Alexandra
I'm working on the first graph still.
Working on the first one, right?
Mm-hmm.
Okay, thank you. And let me change it here. Insert right in here. Let's renumber it. Okay. Who is trying to Genesis? Okay. Now, Benjamin Carvajal, you plot your first graph. Finish graph 1, working on graph 2. Okay, good. Working on 2. 12:22, you still have half an hour. Elizabeth Castellano.
I plotted all three graphs. I'm working on adding the trend line.
Okay, so you plot all the three graphs and now you're working. Okay, working on the trend line. So trend line and R square, right? Trend line. And don't forget R square as well. Square. Next is Natalia. You plot graph number 1, Natalia. Let me put that L6. Natalia is here. Yeah, I see Natalia here. Okay, you're working on the first graph. Okay, thank you, Natalia. Next, Jacqueline Delgadillo. I don't see Jacqueline here. Okay, and Jenny Diaz, did you plot the first graph?
I plotted all three graphs. I'm just working on the R squared.
Okay, did you get the trend line as well?
Yes.
Okay, so let's put here trend line for all three, right?
Yes.
Okay, trend line. Okay, let's put it, yes, and working on the R square. Good. Next one, Valerie Diaz. Are you there, Valerie?
Yes.
Yeah. Okay, did you plot the first graph?
Yes.
What about the second?
Yes.
Yeah. Third one?
Yes.
Okay, trend line?
Yes.
Okay, for all three, right? And R square for all three too?
Yeah.
Okay, good. So what you have to do, log slope, right? Now you have to log the slope there. And let me get that, here you go. Once you get the trend line, log the slope right here for V total, for V2, and for V1. Okay? Keep track which graph is which. This one here is V total. So I'm going to log 1067.7 on V total. 1067.7 on V total. And look at the percentage difference. Very small, 0.97, less than 1%. Okay? That's an example of the percentage difference that we get. Let me see if I can do something here to make it look better. It helps me follow. You go 4, 12, 14, 16, 18, 20, 22, 24, 26, 28. Nope. Oh gosh, I missed out. Let's do that again. 8. Okay, let's see. Yeah, okay. So in good shape here, apparently. Yeah, in good shape. Next, here in line 1, Escalera. Did you plot your graph number 1, Juan? Are you there, Juan? Okay, I'm gonna put a star here under Juan's name. Bianca, you're lucky. Did you? Graph 1 and 2 done. That's good. Yes. Let me. Here you go. 1 and 2 done. Okay, and let me finish here. 18, 20, 22, 24, 26, 28. Good. Okay, next in line. 1 and 2 is Edwin Gonzalez. Did you plot your graph 1, Edwin? Is Edwin there? Yes, 1 and 2, that's good. Next is going to be, and graph number 3. Are you working on that?
Yes.
Okay. What about the trend line for graph 1 and graph 2? Did you get the trend line too, Edwin? Working on it? Okay. Let's put it here. Okay, next. Eli Gonzalez.
Plot all three, trend lined all three, R squared all three, logged the slope for all three.
Okay, so what's the percentage that you're getting for those slopes? Percentage difference?
Yes, for V1, percent difference 0.59. For V2, 0.73. And for V total, 1.68.
1.6. Okay, so it's within the range that I should expect. That's good. And log the slope, and then let's see what else you have to do, huh? Slope logging here, right? So now start working on the units, right? Work on the units, and sig fig. One, two, good. So let's go for Manuel now, Manuel Hernandez.
I did all 3 graphs and I'm working on the rest right now.
1, 2, 3. Did you get their trend lines too?
I'm doing that right now.
Okay, we're doing that right now. Trend line and the R square. Right, next here is Samantha. Are you there, Samantha? Okay, Samantha doesn't seem to be here. Abir, I plot 2 graphs. Okay, I'll get back to you soon. Hang in there, okay, Abir? Okay, next is Joseph. CJ, right? CJ here. I don't see CJ here. And Amber Lopez. All 3 graphs are plotted, working on the trend lines now. Okay, thank you. Why? Working and working. Let's see, Adelie Lopez. Working on the trend line and R square. Okay, so you plot all the 3 graphs, right? It's just working on the trend line and R square. Okay, Genesis. Graph plotted, work on trend line. Okay, thank you. 1, 2, 3, 1 and 1. Working on Mary Michaelian. Are you there, Mary? Okay, Mary is not answering. Let's go for the next one. Galia? I don't see Galia here. No? Okay. Oh, Ramon? Okay. Okay, finish graphing, work on trend lines and R-square. Okay, thank you. 1, 2, 3, working. Next, Taylor. I finished the graph. I'm doing the 6 figs. Okay, so you did all the trend line and the R-square, right? So you're working the 6 figs, the units now. Okay. Oh, did you log the slope, by the way? Okay, what's the percentage difference you're getting there? Point 6, 0.7, and 1.7. 0.6, 0.7, and 1.7. Okay, great, thank you. So you're working on the units and the sig figs. Let's see, Jeremy Pittman is not here, right? And next, Stephanie Ramos. Finish first graph, working on the second. Okay, yes, working on the second, that's good. Alexandra, Leslie Rios. Finishing the 3 graphs, working, okay, good. Why, 1, 1. Okay, let's see who's trying to get in. Edwin. Next in line. Let's see. Let's okay. So Alexandra, well, Alexandra, are you all the graphs there? Did you finish graph number 1?
Yeah, I finished graph 1.
Okay, what about graph 2?
Working on it right now.
Okay, thank you. And Jason Straight.
I'm working on it all right now.
Did you
Nothing's finished.
graph?
No, nothing's finished. I'm still working on it.
Okay, good. We know next here. Gonzalez. Hema?
I'm working on the 3rd graph right now.
The 3rd graph, okay. Why am working? Good. Did you get the trend lines for graph 1 and 2, Hema?
Yes.
Oh, you did, okay. So getting on now, working on the 3rd graph, okay. So let's cycle back here, right? Abir, you told me that, let's see, you finished graph number 1, right, Abir?
Yes, I did the first, second, and I'm working on the 3rd.
Okay, work on the 3rd, that's good. Any questions? Do you have any questions, any difficulty so far there?
No questions.
Okay, good. So, Nestor Alvarado, how are you doing there? Did you finish graph 2? That's good. Let's see, is Nestor here? Okay, look like Nestor is away from his computer.
No, I just finished up the trend line. Sorry.
Okay, so you finish all the 3 graphs, right?
Yeah.
And all the 3 trend lines and R square?
Not the R square yet.
Okay.
I'm doing barely doing the trend line.
Okay, what about the slope? Did you log the slopes?
Not yet.
Okay. Okay, so let me know. Let's go to the next one here. Monte, are you there?
Hello, Professor. I'm here.
Okay. You plot graph 1?
I'm on graph 1, yeah.
Okay, so you didn't get graph 2 yet, right?
No.
Okay. Isabella here. Okay, don't see Isabella. Next is Justus Bowden. We go. Justus Bowden. Okay, finish our plots and work on the R square. Okay. Justus Bowden. Y and Y. Okay, I presume you're also working on the trend lines, right? Next, Benjamin Carvajal. Working on units, that's good. So you will finish all the 3 graphs, is that right? Trend line. Okay, so Bowden just finished the trend line. What about Benjamin? Finish the trend line. Did you get the R square as well? Let's see. Okay, good. So let me go there. So you got R square. The slopes that you got, what, 0.61, 0.77, 1.73. Okay, thank you. And you should be, I presume you're working on the units, right? Okay, so any questions, Benjamin? $12.40, so almost $12.40. Here you go. Elizabeth Castellano. Are you there, Elizabeth?
Yeah, I'm working on the parameters.
Which parameters?
I'm barely starting the one for V1.
Mm-hmm. And let's see, you got all the 3 graphs, right? What about the trend line? Did you get the trend line of the 3 graphs?
Yes.
Okay, good. The R square, did you get?
Yes.
Okay, what about, did you log the slope there in the last table?
Yes.
Okay, how much percent difference did you get?
1.2, 0.6, and 1.1.
1.1. Okay, good. And now you finished the units already?
No, not yet.
Okay, so you're working on that, right? And sig
Yes.
figs too, right? You gotta
Yes.
work on the sig figs. Okay, good. Thank you. Let's go for the next one. Natalia Cordoba. Almost finished graph 3. Okay. So you plot graph 1, you plot graph 2, you're working on graph 3. Let's see here. Okay, and now let's see, Jacqueline Delgadillo. Looks like Jacqueline left. Jenny Diaz.
I finished plotting the slope. I already finished the R squared and I logged the slope.
Okay. What's the value of the slopes that you're getting? What percentage difference for the slopes you're getting?
1.53.
5, okay.
And then 1.17.
1.2, okay. What's the other?
And then 2.1.
Okay, good. So you have good data there. Are you
Okay.
working on the units now?
Yeah, I am.
Okay, good. Thank you, Jenny. Let's go for Valerie now. Did you manage to get the slope, to log the slopes there in the last table?
Yes.
Valerie, okay. What are their values?
0.36, 0.12, 1.06.
1.06. Then again, okay, that you got good percentage differences here. And what about the units? Did you get them?
I'm working on that.
Okay. Don't forget to log all the units there. And 12:41. You have another 9 minutes to go. Juan Escalera, are you there? Okay, cannot hear from Juan. Let's put another star here. Next, Bianca, you're lucky. You're lucky. I don't see Bianca here. Okay. Next is Edwin Gonzalez. Hello, Edwin, are you there?
Yeah, I'm here.
Did you finish graph number 3?
Yeah, I finished it. I'm just working on the slope.
Okay, so you are logging the slopes in the last graph, is that right? In the
Yeah,
last table. Okay.
Yes.
Okay, so you got the trend line, you got the R square, and you're working logging the slopes there in the last table.
Correct.
Okay, thank you. So next one is Ili Gonzalez.
Hey, I've done units and sig figs.
Okay, that's good. And now you need the CL, right?
Yeah.
Okay, make sure you get the CL, and let's gonna put it working. That's the last thing. The CL is the last thing.
I think so, yeah.
Okay, 12:43, 7 more minutes to go. Let's take advantage of this time remaining here. Manuel Hernandez.
Yes, I'm still here. I added the trend line and the R squared.
Okay.
And then
Did you log the slopes there in the last table?
not yet. I'm gonna do it right now.
Okay, working on that. Thank you. Samantha here. Yeah, I don't see Samantha here. CJ. CJ is not here. Now, what about Amber? Are you there, Amber? I don't see Amber here. Okay, so let's see. Arely Lopez, are you there? Okay, looks like Arely is not here either. And next one is Genesis.
I did a trend line. I'm working on the slope.
Okay, you did a trend line and R square as well, right? So you're working on the logging the slope. Okay, and next, Mary. Now it's Mary. Here you go, Mary. Did you plot the graph, Mary? Graph 1, 2, and 3? Okay. Yes, yes, and yes. Did you get the trend line and the R square? Not yet? Okay. Let's put working here. Galia, are you there? Let's see. Galia's still not here. Second. Okay, and next one is Ramon Olivares. Ramon Olivares doesn't seem he's here. Okay, let's put it here. O. And Taylor Fawn. Did you finish the units, Taylor? She working on the units. Okay, working on the units. Okay, and Jeremy. Jeremy is not here, right? Stephanie Ramos. Let's see. Is she working on second graph? Okay. Adding the trend line. Okay. So the next one is Leslie Rios. 4 more minutes to go. Finish trend line. Okay. What about the R square, right? You should have finished as well, right? R square. Okay, good. Did you log the slope? Leslie? Not yet? Okay, working on that. So Alexandra Romanov,
I just finished the second graph.
second graph. Okay. Okay, and working on the third one, right?
Yeah.
Okay, so let's go here. Jason Street.
Yeah, I managed to graph them all.
Okay, and what about the trend line and the R square?
I have those.
You have them?
I have them all.
Okay, what about the slope? Did you log the slope in the?
Yeah, these are the percent differences.
Yeah.
Okay, so for V1, I got 0.706.
Okay.
For V2, I got 2.97.
97. Okay.
And for V total, I got 2.67.
2.6. All right. 2.7. A little bit high, but that's okay. Still showing good. Still a low value. Now let's see. Did you start working on the units already?
Yeah, I'm working on them right now.
Okay. 3 more minutes to go. Jason Street.
Oh my goodness. I'm sorry. I think I answered that all for Alexandra. I'm sorry.
Who is that?
This is Jason. I think I answered
Jason
for
Street. Okay.
Alexandra. So just move all my stuff down the slot. Sorry.
Okay. So you answer for
Yeah,
Alexander, right?
just move it all down one. My bad.
Okay. Just move down right in here. Now I am confused. Let's see. Now I am confused. Alexandra, are you there?
Yeah.
Okay, so just repeat what you told me because now I am I am lost here. Let's see. You finish all the three
I'm working
graphs,
on the,
right?
yeah, I'm working on the third graph now.
Oh, you're working the third graph. Okay. So I logged in the wrong place. Okay, now I know. Let's see here. Okay, and last but not least, right here, Hema, are you there? I just need to log the slope. Okay, log the slope. So, and let me know, go ahead, log the slope and let me know what your percentage difference. I guess that's going to be the last thing we're going to do today. Right now it's 12:49. One more minute to go. I will wait for your percentage in the slope. Can you finish everything else, folks? Okay. And we are almost over here. I need to check what's the problem there in this lab 6 is doing 2 weeks because they're going to do the exam next week. Okay, and I guess we can stop here now and see you next Monday. Okay? And I'm gonna have office hours right now. See you
Thank you,
then. Bye
Professor.
bye. Okay, yeah.
Have a good one, Professor.
You too. Gonna read Dá para juntar tudo? Estou... Estou vou ver. Isso eu já li, agora é minha vez. Vou pensar de voto. Que Carlos, Arthur, Maria Cinco Cavalcante. Arthur, Maria Cinco Cavalcante. Ok, não era para ter quatro. Daniela Valverde, vamos ver. Cento e oito. 2 de maio. Isso. Agora é minha vez. Acabei de dar aula. Acabei de dar aula. Ok. Prometi, entendedor, então. O que significa? Oi, Elas.